this module, you will learn about the modern periodic law and the modern periodic table. You have already learned that the anomalies in Mendeleev's periodic table paved way for the development of the modern periodic table. Mendeleev's periodic table was developed at a time when the internal structure of atoms was unknown. Discovery of subatomic particles and their properties took place at the start of 20th century. Isotopes and noble gas elements were also discovered around the same period. These discoveries warranted improvements in Mendeleev's periodic table. In 1913, an English physicist, Henry Moseley, observed regularities in the characteristic X-ray spectra of elements. On plotting the square root of X-ray frequency emitted by elements against their corresponding atomic numbers, Moseley got a straight line graph. However, he did not observe the same pattern when he plotted the same X-ray frequencies against their corresponding atomic weights. Based on his findings, Moseley established that the atomic number, which is the number of protons contained in the nucleus, or the number of electrons surrounding the nucleus in a neutral atom, is a more fundamental property of an element as compared to its atomic mass, as it defines the electronic structure and properties of an element. Hence, Moseley suggested that atomic number and not the atomic mass should be the basis of classification of the elements. Using Moseley's revelation, Mendeleev's periodic law was modified to modern periodic law. According to modern periodic law, the physical and chemical properties of the elements are periodic functions of their atomic numbers. This means that if the elements were arranged in order of their increasing atomic numbers, elements with similar properties would repeat after certain regular intervals. Thus, many anomalies of Mendeleev's table were removed. For example, the confusion about the position of isotopes was solved. Another anomaly, the placement of higher atomic weight elements like tellurium before lower ones like iodine, was also removed. However, the placement of hydrogen was one anomaly of Mendeleev's periodic table that was still not resolved. On the basis of its atomic number, Moseley placed hydrogen at the top left corner of the table without attaching it to any particular group. After Moseley modified the periodic law, several scientists drafted various forms of periodic tables that focused on factors such as chemical reactions, valence, and electronic configurations of elements. Of all these periodic tables, the long form of the periodic table, which is synonymous to the modern periodic table today, is the most convenient and widely used table. It arranges the elements in horizontal rows and vertical columns based on atomic numbers, while keeping electronic configuration as the basis for periodicity in the properties of elements. Similar to Mendeleev's periodic table, in the long form of periodic table, the horizontal rows were called periods and the vertical columns were called groups. The periods contain elements arranged according to their atomic numbers, and the groups contain the elements having similar outer electronic configurations in their atoms. It has a total of 7 periods based on the highest principal quantum number of the elements in that period. Each period contains specific number of elements as suggested by its principal quantum number. For example, first period has 2 elements. Second and third period have 8 elements. Fourth and fifth period have 18 elements. In both the sixth and seventh periods, only 18 elements are shown in the periodic table. Remaining 14 elements of each of these 2 periods are shown in separate panels at the bottom of the table and are referred to as lanthanoids and actinoids respectively. The number of groups total 18 and are numbered from 1 to 18 as per the IUPAC standards. Let's now understand the periodicity of properties in the modern periodic table. As the atomic number increases across the period, the outer electronic configuration changes gradually from one element to another, resulting in a corresponding gradual change in properties of elements. As the atomic number increases, metallic properties decreases and non-metallic properties increases. In a group, all elements have similar electron arrangement and therefore similar physical and chemical properties. For example, all the elements of 13th group in the periodic table have the outer electronic configuration Ns2Np1 and therefore share similar physical and chemical properties. For example, except for boron, all other elements are metallic, are readily found in minerals and ores, and their melting and boiling point decreases as we go down the group. As of July 2009, the long form of periodic table has a total of 118 elements. All the elements between uranium, atomic number 92, and fermium, atomic number 100, are called transuranium elements. The elements after fermium are called transfermium elements. Both transuranium and transfermium elements are man-made elements synthesized in laboratories using costly and sophisticated equipment. Traditionally, newly discovered elements were named either after their synthesizers or discoverers. For example, the element mendelevium, atomic number 101, was named after Dmitry Mendeleev. Similarly, nobelium, atomic number 102, and lawrencium, atomic number 103, were named after famous scientists Alfred Nobel and Ernest O. Lawrence, respectively. However, for the elements with atomic number greater than 103, different groups began to claim credit for the discovery of the same element, causing naming controversies. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it rutherfordium, whereas Soviets named it kurchatodium. To avoid such controversies, IUPAC suggested a systematic procedure to be followed for naming elements with atomic numbers greater than 100. They recommended that until the discovery of a new element is proved and its name is officially recognized, an element be named based on a systematic nomenclature. This nomenclature is formulated directly from the atomic number of the elements using the numerical roots for 0 and numbers 1 to 9. The roots are put together in order of digits, which make up the atomic number, with IUM appended to it at the end of the name derived. For example, an element with atomic number 118 should be named as ononoctium from 1 is equal to UN, 8 is equal to oct, and IUM, and the first alphabet forms the temporary symbol of the element UUO. After the discovery of the new element is proved, it gets a permanent name and symbol by a vote of IUPAC representatives from each country. The permanent name, thus obtained, might reflect either the name of the country or its state, like germanium, californium, and bohrium. You have now reached the end of this module. In this module, you learned that the English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. He proved that the atomic number is a more fundamental property of an element than its atomic mass. Based on his findings, Moseley revised Mendeleev's periodic law and named it as modern periodic law. The modern periodic law states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. The most widely used periodic table based on the modern periodic law is called the long form of the periodic table. The long form of periodic table arranges elements based on their atomic numbers and outer electronic configurations in 7 periods and 18 groups. Elements having the same principal quantum number are arranged in periods, and elements with similar outer electronic configurations are arranged in groups of the periodic table.